Thank you for joining the third day of the EGI conference. I'm Gergely Sipos, the Head of Services, Solutions and Support at the EGI Foundation. And I'm the chair of this session, which includes a keynote talk from Sylvie Joussaume, Research Director at CNRS Laboratory. Sylvie is specialized on climate modeling, and I'm glad to have her today. As the community she's representing, the IS-INES community, is member of the EGI Council since 2020, and it's great to have Sylvie here to give us an overview of the challenges and the computing services used and offered by the climate modeling community. Sylvie will cover the different aspects of climate modeling, and we'll talk about how the EGI community and its partners helps IS-INES and could help in the future to make the climate mitigation actions more efficient around the globe. So with that short introduction, I would like to ask Sylvie to give her keynote, and I will give you a warning sign if we are getting closer to the end of the session.
Okay, thanks very much, and really thank you for this invitation, which is an opportunity to present you some aspects of climate modeling and with a focus on computing and data challenges. I would also take the opportunity to thank some of my colleagues, Sandro Fiore, Christian Paget, Guillaume Levavasseur. Oops. So I would like, my talk is divided in 3 parts. I would like first to introduce climate change and climate modeling, so the role of climate modeling in climate change. Also present you a brief overview of the international landscape and what are those climate models, and then focus on those challenges in climate modeling. On climate change, I guess I don't have really to remind you that global warming is unequivocal, and here you have the results of the recent IPCC report, the 6th assessment that was just out just this August. And you see below the curve of temperature at the global mean temperature, which is a kind of indicator of the status of the global climate. And this is displayed as the difference with the temperature between 1850 and 1900, which is taken as a reference. And you see that we have a clear increase, not necessarily each year compared to the other, but certainly decade by decade, each of the last 4 decades being warmer than any decade that preceded it since 1850. And in 2020, we reached about 1.28 degrees Celsius versus this same reference. So we have reached a bit more than 1 degree warming compared to what we consider as the reference for the pre-industrial time. In parallel, there is a clear increase of the greenhouse gases and associated with the use of fossil fuel, but also demography and the use of land with deforestation. And you have in gray the sources, so the sources associated with fossil carbon, and in yellow the ones associated with land use. And you clearly see that we reach 40 gigatons of CO2 per year, and with a clear increase since mid 20th century. Below, you see where are the sinks, and the sinks are in the atmosphere, the light blue, which is what stays in the atmosphere. And we have some change in the system, is that about half of the overall emitted is stored in the ocean and on land. So only half of it stays in the atmosphere. But even if it is only half, this has strongly increased the amount of CO2 in the atmosphere, reaching 410 parts per million in 2019, which is a 48% increase since 1700, taken as the pre-industrial reference for the greenhouse gases. And this is clearly unprecedented in the last 800,000 years. So how to say that the two are, it's clear that the increase of greenhouse gases tends to warm the system, but to really be sure to really demonstrate or investigate this link between the two, we use the climate models. So the modeling of the Earth's climate system takes into account the atmosphere from top left, the atmosphere, the clouds, the winds, below all what happens in the ocean with your temperature gradients, exchanges of salinity and currents. And then top right, you have the land, representation of land with vegetation and the air going from the ocean to the land for water vapor cycle. And below, bottom right, you have the greenhouse gas emissions. So they're a different composition of the atmosphere. So those models are represented over the sphere decomposed in the atmosphere and the ocean, taking into account the atmospheric and the ocean circulation and all the heat and water exchanges. Those models are quite key to understand what happens, but also predict how climate can vary and change. This figure represents the status of where we are for the explanation of this observed warming. In black, you have the observed warming that I just showed you, and in orange and blue, you have two sets of ensemble of simulations. In blue, you have simulations by a range of models that only include natural forcings. Those natural forcings are from solar and volcanoes. And you see that there is variability in the system and the models is reproducing it, and that we can explain some little, for example, some small cooling associated with volcanoes. But on the overall, we are absolutely unable to explain the big increase that is observed in the atmosphere. If you look at the simulations in pink, or I don't know exactly what is the color, you clearly see that if we add superimpose on those natural forcing the human, the forcing associated with human activities, which are the increase of greenhouse gases, but also the small particles, the aerosols that are emitted in the atmosphere, you see that in overall, the models are able to reproduce the main features of the main increase. And that's one key element that allows us to say that it is unequivocal that human influence has warmed the atmosphere, the ocean, and land. And key climate models play a key role in understanding and in explaining what happens and understanding the mechanism behind. The models are also quite key to be able to say anything about the future by doing simulations of under different future emission scenarios. And here you have the last version of it from the IPCC 6 assessment report, where you have different sets of scenarios. The red ones are the high, red and purple ones are the high scenarios where there is practically no policy of reducing emissions. And you can see that the different models provide an estimate of a further increase by the end of the total increase by the end of the 21st century that reaches about a bit more than 4 degrees, with a range of uncertainty depending on the range of responses by the different models. If you have intermediate scenarios in yellow, but that also include some policy and reduction of emissions. And in blue, you have the low scenarios that include quite a strong reduction in the emissions. And you see that depending on how much greenhouse gases will be emitted, as well as aerosols, we obtain a range of values, and the climate models are really the ones that are behind what we can say about possible future changes. The idea, the agreement of the COP21, which was the Paris Agreement in 2015, strongly advocates to limit to 2 degrees. And you have the 2-degree line, which is emphasized here, compared to pre-industrial. So we have already reached a bit more than 1 degree. And we have really to be in the range of the blue scenarios if we want to limit to 2 degrees, and even it is recommended to limit to 1.5 degree. So you see more the light blue curve corresponding to this target. Why we have those advocacies to limit and to this agreement to limit is to limit the high risk associated with those climate change. The risk can also be evaluated with the climate models that provide not only global curves that as I show here, but also the geographical distribution for here different targets. So you see the temperature change if we reach a 1.5, a 2 degree or a 4 degree, or even below the precipitation change for 1.5, 2, and 4 degree. For the temperature, you see the more we have, the highest the warming is, the highest, of course, the warming is on the different in the different geographical distribution. But with a similar pattern at each time, the warming is higher over land than over the ocean, and higher in high latitudes, where it can reach more than 7 degrees if we reach the 4 degree global warming. Below, you have the changes in precipitation. In blue, wetter. In yellow, brown, drier, where you see that once again, you have similar patterns with different warmings, but stronger amplitude when you reach 4 degree warming, whether drying of some regions like the Mediterranean regions, higher precipitation in high latitudes. And those changes are not only coming as mean, but also changes in extremes with more intense precipitation, more heat waves, and also more drought events. So that's all those risks that lead to that yields to the agreement to limit to 2 degree or even 1.5. So those models are really behind those estimates, not only for what could happen under scenarios, but also what is the amount of CO2 that can still be emitted up to now. Sorry, we have emitted 2,390 gigatons of CO2 since the start of industrialization. And if we look at how the curve above, you see that temperature change is highly correlated to the total amount of cumulative CO2. So at each time we accumulate CO2 in the atmosphere, the temperature increase. If we are in the blue scenarios that were the lowest, you see that we limit the temperature, but we also have a limited amount of CO2 that we can still increase. Typically, to reach 1.5, if we want to limit to 1.5, we have to reduce by 45% in 2030, and we have to have a net zero emission by the mid-century, so 2050. If we limit to 2 degrees, the net zero would be at 2075. But so the more we accumulate, so if we continue to accumulate CO2, we will reach 3 to 4 degree warming. So it gives a way to estimate how much we can still emit corresponding to each climate target. So the models are quite key behind all those estimates and all those climate policy. On what are those climate models and what is the international landscape? Those models that we often call Earth system models encompass the physical components of the atmosphere, the land, the ocean, coupled together with also the sea ice, but also more and more the biogeochemical cycles. So the atmospheric chemistry, the transport of gases, of aerosols, vegetation dynamics, which plays a role in the carbon cycle, as well as the ocean biogeochemistry in the ocean, so the carbon and the biology that are key for the carbon cycle as well. And those overall model, I estimate it's about 1,000 man-years of development cumulated over the last 30 years. Typically, the recent Nobel Prize to Dr. Suki Manabe. Manabe was really one of the first to develop those physical components, ocean atmosphere general circulation models on the left part, and was recognized for his role with this Nobel Prize. Those models have a strong legacy, which is an issue for to have them evolve with different technology with computing. They are based on physical laws, so Navier-Stokes conservation laws, and they include parametrizations for the parts that are not resolved explicitly, so where we do not necessarily have equations that we can solve, like the clouds, the surface fluxes, radiation, subgrid scale processes that are parameterized according to their spatial resolution. The spatial resolution is evolving through time, depending on computing power available. At the beginning of the century, it was more in the 200 kilometer, then 100, and now most of the models are in the 100 kilometer, but the highest range reach around 30 kilometer. And you see that the spatial resolution is quite key to resolve their topography. Here, the Alps, and the land-sea contrast as well. The way we are organized are through international coordinated experiments under what is called the World Climate Research Program, WCRP. And we have cycles of those organized by WCRP, which are faced with the IPCC assessment reports in order to use the results of those simulations in those assessment reports. So typically the last one, the recent one, phase 6 of CMIP, CMIP 6, encompasses 23 different model intercomparison projects, those MIPs, and corresponds to 20 to 50,000 simulated years. We reach things like 100 million core hours used to produce them, with 1 to 10 petabyte produced per model, even if not all of those data are shared between all the groups. Those simulations are quite key, provide a key reference base to understand the changes, but also to evaluate the models and to project what can happen in the future. So those are the 3 pillars that are really key to the community and do a strong basis of the climate science. Typically, for the CMIP 6, the core experiments, we have about 30 modeling groups worldwide, and with 8 in Europe. And the European project EASINESS that I coordinate, the infrastructure for the European Network for Earth System Modeling, coordinates the contribution to the international database with those different European models. And you have 1 in Russia, 1 in Canada, 5 in the US, 7 now in China. They have grown through time, 1 in Taiwan, 3 in Korea, 2 in Japan, 1 in Australia. So you clearly see that it is really worldwide. At each time, for each of the modeling group, you can have several versions of the model, different resolution, low resolution, medium, high, different complexity, either only the physical components or including the biogeochemical cycles, so different versions of the model, so leading in overall here to 59 different models. The data are shared internationally through the grid, a grid called Earth System Grid Federation, which has been launched now some I would say probably really it was launched for the CMIP 5, so the last exercise. And that is really a way to share the overall data all together. You have the nodes, the different nodes that exist that are displayed on the map. And you have on the right the peer-to-peer system, which is represented with some of the nodes just being data nodes, some other nodes providing index, identity provider, and compute compute facilities to compute to do analysis of the data. This Earth System Grid Federation, this includes 13 million of data sets and reaches now 30 petabytes with about 15,000 registered users. All those data are fair, they are completely open access and include common data and metadata standards. This is a multi-agency support. This is supported quite a lot by the US with the Department of Energy, NOAA, National Administration for Ocean and Atmosphere, the NASA. And in Europe, we are the ones that contribute to it, EasyNess, and NCI is for Australia. And this is really a shared development internationally to support the overall database. So these MIPS experiments, they have evolved through time. They started basically in the 90s. It was launched in 1995. At the start, it was mainly some control runs with just 1 gigabyte of data shared, just central storage. Then the second phase in 1997 included some increasing CO2 experiments, 0.5 terabyte shared. The third one shared 35 terabytes, still centrally, and it was used in 2007 IPCC reports. And since the CMIP5 and CMIP6, so since the last 2 cycles, this is now shared with a grid, system grid federation. And if CMIP5, we were in the range of 1.5 to 5 petabytes of data, the 2 numbers being with or without and with replica. And for CMIP6, we reach 21 petabytes, including replicas. So you see that in the 30 petabyte of ESGF, CMIP6 is now really the biggest contribution with 21, CMIP5 the second with 5, and the rest are some other experiments that are shared within this Earth System Grid Federation. One other aspects that can be also of interest in the way we have shared the data in the community. At the start, it was really only data were only accessible on sub-project basis, so you have to declare for which use you wanted to have access to them. CMIP3, it was open and free for non-commercial, so still not restricted for non-commercial. And then CMIP5 was much more open, and just very few had closed access for non-commercial. With some, there was still, at that time, you needed to have to be registered, and CMIP6 now it's completely fully open with no restriction. So the community has evolved through time, and it's quite important because those data are quite extensively used to assess climate change and for policy at the international level, and also to derive some impact studies to understand what happens on hydrology, on energy, agriculture, health, and so on. If we look at the data from the European nodes, this is the activity under EasyNess. You see here the statistics from EasyNess 2, that was the previous phase, started in 2013 and now reach until September 21. And you see the number of data that are, the amount of data shared each month, downloaded by the European system grid data nodes. And you see that now we reach values of the order of 400 terabytes exchanged each month just by the European data nodes, with users being either EU users in brown, and in yellow, all the other continents also accessing data. And easiness 3 is mostly constrained by CMIP 6. Easiness 2, it was CMIP 5, but also what we call codex, which are regional simulations performed based on the global simulations, but on limited area regions. If we look where the different data are downloaded, you see above that it's quite heavy in the Northern Hemisphere with 10 petabytes of data that have been downloaded in the US, 8 in Europe, 5 in Asia, and even some in the Southern Hemisphere, but we are more less than 1 petabyte. And if we look at the number below of the distinct clients of those data nodes, which are an average between the European nodes, because we cannot be sure that they are different between one node to the other, but for each node there are distinct users. You see that we are reaching 7,000 users each month, and as an average, because we don't know if they are the same or not between the different nodes. Those data are then quite key to inform on climate and really serve as a key reference, in particular for the evaluation of those models. And you have on the left, you have the correlation with observation. So when you are at 1, you're good, really very good compared to very similar to observations. Below it's less good, and you have different variables like air temperature, where you see the first one that it is very good for all the sets of models, all the generation of models. For precipitation, you see that when we go from the brown, blue to now AR6, which is in orange, we have an improvement of the estimates, but you also see that it's less good for precipitation than for temperature, and you have a range of estimates according to models. You also see with the gray bullet, that if you look at alternative observations, there are also uncertainties between the different sets of observations. So it's not that easy to really have a good estimate of the observations for precipitation. If we go to the two other next columns, the first one is outgoing long wave radiation, quite good. Then the short wave. And you see that the short wave have more uncertainty, and that's the main source of uncertainty of the range of response of the models are associated with the clouds, and especially the response in the short wave. And then the next one is sea level pressure. On the right, you have the observations in black over 1850 and 2020, the same as I showed at the start of the talk, and you see that the different sets are able to reproduce the main trend, with the last one being the blue one, CMIP 6, being quite close to the observations. So those simulations, those sets are quite key to help us evaluate the models. I would like now to focus on the challenges in climate modeling, starting with a World Climate Research Program strategy plan, which has been issued recently, and for which models play a role together with, of course, observations and different ways of understanding how things work. So on those topics, there is the need to better understand the variability and changes in the coupled system, to better predict seasonal to decadal time scale, and this is quite key for adaptation policy, but also to better understand uncertainties and feedbacks in the system, which is quite key not only for adaptation, but also mitigation, which is the more longer term response of the system, so until for the century and even longer. And also bridge the gap with our society and to be able to provide an information and knowledge which is relevant for a decision. Behind, for the modeling part, behind the the capacity that we have to perform simulations, computing is quite key, and computing associated to that, there are 4 different aspects that are where computing power is quite dimensioning. The spatial resolution, for sure. When we increase the spatial resolution by 2, we need a computing increasing by a factor of 8. Complexity, if we include the carbon cycle, the aerosol chemistry, the biosphere, that adds to the complexity about a factor of 5 to 10. Duration of the simulations, if we want to understand the viability of system, this viability occurs on a quite wide range of timescales, from interannual to decadal to multi-decadal, even multi-centennial. And so to be able to have long enough simulations, we talk about a measure which are SYPD, which are simulated years per day. And we need per day of computing to be able to simulate 5 to 10 simulated years per day. And then the ensemble size since to document internal viability, to quantify uncertainties, we need ensemble of simulations. What I'm going to illustrate are not all those 4. I'm going to concentrate on resolution, the first one, and ensemble size, and then we'll focus on the data side. So to illustrate the spatial resolution, I have taken an example from one of the MIP, which is called IRS MIP, which are the simulations with the highest resolution, reaching those 30-kilometer resolution, and which was supported in a European project Primavera, where you see on the left simulated tropical cyclone paths, where you have the number of intense cyclones, and you see the impact of different resolutions. You have the observations, bottom right, and you see from 160 to 25 that when the resolution is increasing, so more smaller size and bigger resolution, we have a better representation of those patterns. If we look on the right, those are biases in precipitation variability in one land area, like the Danubius River. And this compares CMIP5, which was the previous set of simulations, regional models, which are much higher resolution, but only limited area regions, and CMIP6 at high resolution, showing at each time that the bias is reduced. So clearly, spatial resolution allows to have a better representation of regional features, and that's an important aspect for adaptation. But it has a cost, and if we look here, these numbers given by the UK Met Office study in this paper, you see that going from the first line to the bottom line, so 250 kilometers in the atmosphere down to 50 kilometers, so increasing the resolution by a factor of 5. You look at the nodes, you go from 12 to 90 nodes for the atmosphere, so you have basically an increase by a factor of 10. But a speed that increases by a factor of 10. So it's nearly a factor of 100 going to a resolution of 5, increasing by 5. You have a factor of 100 in, going much less simulated years per day, and also a factor, an increase in the data, which is conditioned by also the number of output you want at higher resolution. You want to have a more frequent analyses to investigate the extreme events. Let's see also the variability. Here you have the observations that I have already showed you, and different sets of simulations with the French model IPS from IPSL, from the other French model from Météo France. And around those set of simulations, 32 and 10, you have one emphasized for IPSL and one emphasized for Météo France, showing that we have a range of paths And one is a bit nearer than the observations, but we can never reproduce exactly the observation. The system is chaotic and we need to document its variability. And of course, when we simulate the future scenarios, we have also this variability, and it's important to document a set of simulation and not just one, due to represent this variability. And the more simulations you have, the higher the computing time you need. It's also the more simulations and the higher resolution and number of simulations, the more amount of data you have. On the left, you have an estimate that was published by John Overpeck in Science in 2011, showing what we estimated at that time as the deluge of data starting 2010 to 2030, with the satellite and radar data in blue, and the amount of data from models in orange, with a limit of 50 petabytes shown, and showing that both were planned to be increasing nearly of the same order between modeling and satellite data, which are quite heavy on the amount of data. On the right, you have one status done by NASA, by Sadar Lee in 2017. So you have 200 until 2016, same colors. And you see that the 50 petabyte is even reached, it's about what was planned. So, but just for NASA, reached in 2014. And you see that for NASA, the amount of model data is even bigger than the satellite data, which is quite impressive. So we have clearly to deal with this large data workflow, and which is quite an increasing complexity to deal with, which requires parallel I/O, on-the-fly processing, compression, reduction of data, and more computing near data. And that's where I would like now to focus, is how do we deal with our analysis of the data, and how do we deal with all those management of our data and the link with EGI. On those graphs, you have the traditional, on the left box is how we process the simulations, and we do a lot of analysis on our HPC platforms, and that's relatively internal to the community. And then we display the data on the Earth, a part of the data on the Earth System Grid Federation. And we also have more and more some pools of data where we gather a subset of the data to allow to have computing associated with the data, so with multimodal analysis platforms. Our community face quite a large range of use. We have the climate science to understand and predict past, present, and future climate. So basically all the diagrams, all the results I showed you were basically coming from the climate science, but there are also all the climate impact community with sectors, different sectors, using the input from what comes out from the climate simulations to force some sectorial models for agriculture, hydrology, energy, health. And we also have more and more climate services that use this information for decision, for mitigation and adaptation. And we have to deal with all those. So on the multimodal analysis, we have our data are stored on different nodes, but if we want to do the analysis, we have to have the data gathered to be able to compute different analyses, averaging, subsetting, climate diagnostics and indices, downscaling, also putting the data at a higher resolution by downstaining methods like statistical downscaling, bias correcting to force impact models. So we need to correct of some bias, or otherwise the impact models will have some issues. Processing and visualization tools. So typically all the maps that I showed you, the charts I already showed you, needs to be done by using those Earth System Grid Federation. So more and more what we develop, and we have 4 of them within EasyNess, are compute services, climate analytics services, ECAS, INES Climate Analytics Services, where we have 4 sites like in Italy, or Germany, France, and UK, that also afford for some computing resources. We'll go and fetch the data at the data nodes and allow to have computing near the data stored locally in pools and accessed by different interfaces. One of those interfaces is a platform we have developed for impact research to explore climate data and perform analysis, which we call Climate for Impact Portal, where it is to simplify the different way to access to variables. ESGF is completely open, and you have same names for all the models, but it's not necessarily very user-friendly. So this one is more user-friendly to ease the community, which is less used to directly work on climate model output. And that allows also to perform different indices, to do some processing directly on site, and as well as downscale the information at more regional scale. So this is something that has been developed within EasyNess. We also work with Copernicus, the Copernicus Climate Change Service for the climate service aspect. Copernicus brokers on a System Grid Federation to provide access to the projections, which are both global and some are regional. And this completely relies on the expertise from EasyNess, but only provides a subset of simulations, historical and projections, and a subset of models and variables. This has been done for CMIP 5, is ongoing for CMIP 6, and there are also some regional simulations that have been added for Europe. So this is a way to provide a subset available for a much larger community and the climate services. On one key aspect is to see how we can really strengthen this climate analytics service and also make it available to a wider community. This was the objective of EOSC Hub that has benefited from Indigo Data Cloud, from EGI and EUDAT, interfacing different data sources, including Earth System Grid Federation, having a work environment with some software here for visualization called Ophidia from Italy, and allowing the users to share their data using EUDAT and OneData, and benefiting from different supporting services from EGI and EUDAT. So that was started in EOSC Hub. This is a thematic, one of EOSC Hub thematic service, and is working. And we also have a collaboration within the DARE platform that is more using the Climate for Impact. EasyNess SIG4I is the Climate for Impact, as an interface to go and fetch the data from Earth System Grid Federation, then uses the DARE platform to use the cloud computing aspect and exchanging the data using EUDAT. So really being a way to use cloud resources efficiently within in collaboration with EUDAT and this DARE platform. Those are both EOSC projects under EU. On the current, there is now a current project called EGI ACE that goes from EOSC Hub and goes a step further, and that makes really investigate and further strengthen this idea of INES data space, so the concept of data space, so being able to access ESGF data through EasyNess, and having a data space environment to allow the users to use whatever they need as different software and environment and visualization, and in compute and easy access facility. So this is developed under EGI ACE, and you have on the right this INES data space that is now starting to work and accessing some visualization capacities. So the landscape is a bit complex. This is my last slide before the conclusion, and I've tried to gather that on a tentative schema. So we have the INES research infrastructure now under EasyNES, and we plan for a sustained research infrastructure beyond the European funded project. There are also some environmental research infrastructures at the top, ENVRI, and INES is part of this ENVRI ensemble of environmental research infrastructures. And we have EOSC as a way to provide, that should help us really provide more easily computing, access, storage, and facilities to manage, to deal with those data. So we are developing a cloud approach with the DARE project, and there is now a new proposal, NRISC, with the environmental research infrastructure, in which EGI is included, that will allow to develop a data space which is also encompassing the observation research infrastructures, not only the modeling. We have the data space associated with modeling, where high performance computing is quite key for analyzing the results, which is with EGI ACE. We have the concept of digital twins, where the models, but together with our more sophisticated analyses, allows to have a better twin digital information available to user. And there is an inter-twin proposal that have been set with EGI. And all that should allow in the future to, that's a bit how we see this link with EOSC as a way to provide, to strengthen the capacity to exploit more easily all those data, especially for communities that are less directly experts in climate modeling. And for the link with decision and policy, we are already working with Copernicus C3S. Destination Earth will start. It's still a bit difficult to really know exactly how it will be, but we will certainly interact with this Destination Earth. The climate models that will be used in the digital twin of Destination Earth will be some of the ones used in EasyNES. There is a collaboration within the Intertwin proposal to also have a possibility to evolve and make this concept of what is proposed in Intertwin in link with Destination Earth. And of course, for EasyNES, we interact internationally with Earth System Grid Federation. So a kind of tentative schema. And to conclude, I would like to reinforce that really climate models are the core of climate information for mitigation and adaptation, but also needed for understanding. We don't only need those models for policy, but also for understanding climate. And to address the climate research challenges, we need a sustained European climate modeling infrastructure to support the data, the development of codes, the sharing of expertise. And this is key for the IPCC assessment reports, but also services like Copernicus. On the data and computing challenges, for high performance computing, I wanted to show that we have a range of needs, such as spatial resolution and large ensembles. But something that I had no time to touch is that we need to prepare for future architectures. We have legacy codes, complex workflows, and now are arriving more and more these accelerated computers. And it's quite a challenge for us to adapt to those. For the data, we have, with our increasing complexity ensembles, to manage more and more large amounts of data near high performance computing. We also have to ease the access and democratize as much as possible the analysis of those large climate data sets, like multi-model ensembles. We are preparing for a next generation of ESGF. that will better account for new clouds developments, that will be easier to implement, that will also improve data publishing, and in link, and of course in link with easiness and all other collaborations, and also enable complex analyses like using artificial intelligence. For all that, collaborations are quite key. Of course, System Grid Federation, so in particular with the US, but also Copernicus, but also EGI. And I hope I showed you some examples of our collaborations that are already quite interesting. And we can hope that the European infrastructures like EuroHPC for the high performance computing part and EOSC should help in the future, being sure that we make the best benefit of all those large climate data sets for the largest possible community. So I would like to thank you. You can know more about easiness. You have the references that are given here. Thank you.
Thank you, Sylvie, for this very informative talk. And we have a few minutes for questions. I see that a couple of questions already came in through the chat. The first two actually came in from Tiziana Ferrari. The first one is about, with the increasing amount of data federated worldwide in ESGF, how researchers in climate science get access to such data? Is it download and processed in their labs, or is it processed centrally?
In fact, we have the two aspects that are done. So in Europe, more and more, the way we process is that we avoid that each user download the data at their own on their own computer. And so we have data pools that allow users to have a set of multimodal and data that they can process with computing associated. This is done in Germany, in the 4 nodes I showed, so also in UK, France, and Italy. But you also have some more users that just download the data they need and that process them. We think that we would like in the future to be more able to have the data, to have more processing near the data, or not necessarily. The problem is that some of the processing, like subsetting or averaging, should be done where the data are, and just download those subset of data. And then, but then anyway, you need to have access to data that are in different nodes. So we have at some point a need to gather, and how much cloud technology should help us to do that more in the future, and how much what is tested now done with EGI can help is quite an issue also for us.
Thank you. My colleague enabled the microphone for those who want to ask questions. So maybe I see that second one is also from Tiziana. I don't know if that question was answered in the meantime. Well, Tiziana, you can ask that if you wish now.
Thank you, Sylvie. I think you already explained that in the last part of the presentation. Thank you.
Okay, thank you. The next came in from Herman Heisling. So Herman, can you please unmute yourself and then ask this question?
Yes, thank you. Sylvie, it's a question about the relation between the models and the Navier-Stokes equation. You mentioned your models are based on the Navier-Stokes equation. How far, and you mentioned the resolution power, that it is of the order of 100 kilometers. Is this far distant, or is this sufficiently close already to imitate the Navier-Stokes equation?
Yeah, we can resolve numerically the Navier-Stokes equations, of course, not with some parametrization of the subscale. When you are at 100 kilometers, what is under that needs to be parameterized. and that's some diffusion that is added typically. So yes, in the atmosphere with 100 kilometer, you can, of course, if you increase the resolution, it can be better resolved, but no, yes, it is possible. In the ocean, we need a bit higher resolution because the structures are smaller, so we need more resolutions in the we tend to have more when we have 100 kilometers in the atmosphere, 25 in the ocean typically. So at each time we are higher resolution in the ocean than in the atmosphere. When one of the key gap when we there is a target in the community to reach the kilometer scale, but it's not much for Navier-Stokes, it's more for the clouds. So if we reach this kilometer scale, we would be able to resolve explicitly the convection, the large convection that occurs in the atmosphere, whereas when we are at 10 or even higher or 100 kilometer, we have to parameterize those clouds. So that's more for the clouds that we have this. If we want to be even better for Navier-Stokes, we would have to be even smaller resolution than the kilometer.
Thank you. There are a couple of more questions, so just quickly let's try to answer as many as possible because I'm conscious of the time. The next one came in from Eleonora Testa. Eleonora, can you ask this question?
Yes, sure. Bonjour, Sylvie. My question was related to this last slide. In any case, in which I saw that artificial intelligence was used and largely used probably to develop quickly models and complex analysis. So because EGI is particularly interested in this moment to understand if we can support more in this area, artificial intelligence and machine learning, I would like just to ask you how important is this the usage of technology, and if you like the idea that we can support more in this part.
The statistical approaches like neural networks has been used for long in our community for the analysis part, and now there are even newer approaches, or it's even further developed. For the parameterization, it's more new. It's just it's more starting. It was not used, but the problem is to have enough data to train such a parameterization. But it's something that is now a bit starting. Although it's not that obvious that you can train something on present climate and that it will be valid for a different climate. So it's really, we have those two sides, the analysis of the data and the training for the parameterization, but it's more future. For EGI, typically for the analysis of data, the data spaces can really be a place where indeed people can perform AI analysis of the climate data sets, for sure.
Thank you. I see there are so many questions in the chat that we are already late, and I don't want to eat everyone's time from the break. So what we do is we keep the room open, and Sylvie, you can answer the questions in the chat if you still could dedicate a few minutes.
Okay.
Right?
Okay.
But then we can let the people have a quick break before they enter for the next session.
Okay, so I start with Sebastian. Okay,
yes, Sebastian is the next one. Yes,
exactly. So I can stay connected. I answer to the questions. Okay.
Thank you very much, and thank you again for this very informative talk.
Thank you for your invitation and your interest.
Thanks for the others for listening. Bye, and have a good rest of the day.
Thank you. Bye-bye. I know.